lecture at Troy University on quantitative methods. So I spend a great deal of time teaching undergraduates about the basics of statistical methods, the interpretation of them, and just getting them prepared to move on to careers as data scientists. My other gig is I'm a teaching assistant for the Machine Learning 2 course at Southern Methodist University. I've been doing that for a little over a year, and what we do is we focus our efforts on teaching some of the more advanced machine learning concepts. The third gig is probably the one that I'm passionate about all of them, but my personal chosen career path is that of a reinforcement learning researcher. Who has heard of reinforcement learning? Give me a thumbs up. Okay. Out of you that have heard of it, who's ever run reinforcement learning algorithms before? Okay. Who has driven in an autonomous vehicle before, a self-driving car? Anybody? One person? Okay. So what we're going to talk about today, the technique behind, there are several techniques behind reinforcement learning, and today the way we're going to set things up is I'm going to talk for a little over an hour and then leave some time for you guys to have questions. I'm not going to presuppose any knowledge about reinforcement learning or the way self-driving cars work. So I'm going to give just a good broad introduction in the span of a little over an hour. And then hopefully what I've done by the time that I finish this is to motivate you to try some reinforcement learning algorithms on your own, because I do have a resource for you, and I do have you, I've prepared some code for you just to test on your own. So I'm going to be speaking today, and let me also introduce, and this thing has no name yet, to some of my colleagues. Noel, you'll know some of them. I asked them to help me with a name, but they were so profane in their recommendations that we're not going to use any of them. So maybe this group here will be more enlightened than the other people that I do research with, because they couldn't come up with a name that I could say in front of my kids. But here's the part. Notice it has AWS on the side, because to use this car, you have to use Amazon Web Services. And we're going to look at that today. We're going to look at an actual demonstration of it. But here's a car. Right in the front of the car, look at the car here. This looks like the front, doesn't it? Doesn't it? But this is the front. This is the front here, because you have two 4 megapixel cameras on the front of this vehicle, and it's of course wireless, and the software can be downloaded wireless from the model that you run in Amazon Web Services. That'll be made a little more clear as we go through this presentation. This is called a LiDAR, and it just is a sensor, and it senses if you're moving to the left or to the right, or if you're close to hitting something. When you turn it on, it spins around and makes a bunch of noise. But here is the vehicle right here. And again, I'll send you a case of beer if you can come up with a good name for me. I'm not creative enough to do that. Okay, cool. Let's have a conversation about reinforcement learning. What is it? Reinforcement learning is, think of it like this. Somewhere right now, there's a young gazelle that's being born, okay? Right at this moment, you have a young gazelle that's being born. It's coming out of its mother's womb, and it doesn't know how to move. It certainly doesn't know how to run, but it starts moving, and it notices that it moves too far to the right, then it falls down. Too far to the left, it might trip up. But within 20 minutes, within half an hour, that gazelle can run 20 miles an hour. That's an example of reinforcement learning. Good or bad behavior is reinforced. With the car, which you'll see in just a moment, good behavior on a model is keeping close on the lines, correct? And bad behavior, points taken away, are with vehicle merges off to the left or to the right. Now, to do that, reinforcement learning does hang on, guys. I'm looking at. I've got something open for you guys, and I wanted to make sure it's still what it's supposed to. I've got some Python running in the background. Okay, sorry about that. We're good. Any statisticians in the crowd that have had some experience with Markov decision processes, the way the Markov decision process works? We're not going to get too far into the math. We're going to touch on it. But with Markov decision processes, you have exploration and exploitation. Anybody here watch any fans here of the Tour de France? Anyone? Okay. They have and here's a way to put this into terms of exploration versus exploitation. So in the Tour de France, you don't just have one cyclist riding, okay? You have a team of cyclists that work together. And you have one cyclist who's the lead cyclist. And then you have other cyclists where their only job is to keep people that would be trying to catch up to the leader, to give them somewhat of a false sense of security as to how fast they're going. So in other words, you're keeping up with one person, but the person who is further ahead in the race is substantially further ahead, but you're only focusing on the person who's closest. So what you're doing is you're exploiting versus exploring. If you were trying to find that cyclist who's ahead of the race faster than everybody else, you would be exploring a new possibility of something that might be better versus exploiting those that are around you. That's the way multi-armed bandits work, which is important to reinforcement learning. You'll see that more because the term that you're going to hear me say quite often is reward and value. The reward is something that's instant gratification. Value means finishing the race on top. Okay, that's just conversationally right there. And the way we're going to make reinforcement learning easy, and like I always enjoy saying, I'm going to trick you guys into getting a good hold on reinforcement learning because I want you to think about it and look at it in the space and in the spectrum of self-driving cars and being rewarded or being punished, because that's what reinforcement learning truly is. Can I share my screen now, Noelle?
Yeah, you should be able to. Okay,
cool. I believe I sent you guys a copy of this PowerPoint, and for some reason I didn't. Let me know. Let's go through this slideshow and just start. We're going to start with just some basic nomenclature about reinforcement learning, and then we're going to dig a little bit deeper into how it specifically plays with Amazon Web Services. So this first portion is going to be generally about reinforcement learning, and we're going to almost duplicate some of the material so I can give you a very specific example with self-driving cars. Here you have, here's some terms. We need to get some terminology out of the way. You have an agent, which would be a robot or a self-driving car. This is an agent. You have a state or an action. The state for this robot is the robot standing there, and the action would be the robot moving. The environment would be the entire world. For a self-driving car, which you'll see in a moment, the environment is a racing track. And then you get rewards or punishments for the state. Okay, so an overview again, what is reinforcement learning? Where did it gain prominence? Terminology, there's a lot of new terminology in there. We're not going to talk about the Bellman equation, multi-armed bandits, deep Q learning, or any of the math behind that. We're going to abstract a lot of that away and just acknowledge that they are there and briefly discuss what they do. I will tell you, and this is why someone like Noelle is so perfectly suited for this, because she has such a strong background in math. This field, it is mathy. It's mathy. It relates to it has strong relations to dynamic programming, as well as dynamic, as well as just algorithms. And I'm sorry about that. I've got something to show you guys is running in the background. It keeps messing with my screen. So sorry about that. We're going to talk about how reinforcement learning is used, and then toward the end, I'm going to give you guys some sample code and a website just to get you started. I would feel remiss if I went through this topic and at the end could not say, hey, here's a way for you to participate. Okay, I would be hard pressed to want to give a presentation like that. So I do have a way that if you are interested in this, you have some code to mess around with after this presentation. Okay, so far in your studies, you guys have talked about supervised learning. Okay, where think of a CSV file where you have X as a data, Y as a label, and the goal is to learn a function to map X to Y. So that's supervised learning, which some of the algorithms are classification, object detection, regression, and image captioning. Not talking about deep learning here. I'm just talking about supervised learning. You've been exposed to that where you would classify this picture as a cat. You've also been exposed to unsupervised learning where the data is not labeled, nothing but data, and you're looking for some type of underlying structure. And typically you could do that with principal components analysis, SVDs, clustering, different types of feature learning. You do that with you can do that with supervised learning. What we're discussing today is somewhat of the, and me personally, with reinforcement learning, I'm taking a chance in my career that reinforcement learning might or might not be the space to be. I'm taking a risk as an academic and spending the time to study this. But one thing I will say about it is it does bring in a lot of cross-disciplinary units, such as statistics, linear algebra, calculus, and elements of deep learning. So that gives me quite a bit of security because there are so many different things that you're having to master if you're doing lectures on reinforcement learning, or if you're doing that is your trade. It took me probably a year to truly be able to function as a reinforcement learning researcher. There were things that I had to go over again, particularly in the math area and then the area of algorithms, but before I was really able to get comfortable doing this. So this is one of those things where you don't just passively, I'll just say it like this, don't ever go on a job interview and say that you have strong reinforcement learning skills because you'll be eaten alive if you meet with someone who actually does. It's a steep learning curve, but I always like to say this, if I can do it, I feel like anyone can. It's just a matter of putting the time in, and it's been quite a time investment. So reinforcement learning, what we're doing, and think about this to set it up right. Let's think about our vehicle. Let's think about our vehicles. So you have problems involving an agent, the vehicle, right? Interacting in an environment, the track, and you provide a numerical reward. That's something you're going to see a little bit different. You have different measuring mechanisms in the world of reinforcement learning that you don't have with supervised learning. Supervised learning, you can look at R squared, you can look at your root mean squared error, and that's how you determine whether your model is working or not, comparing the bias versus variance and several other statistical measuring techniques. It's a little different with reinforcement learning. In some ways, it's a little more simple. It's harder to get to the equation, but as you'll see in a moment, it's based on a reward system. How well is this car doing? Okay, well, we can measure it like this. how fast can the car finish one lap around the track. You can measure the reward system. I mean, that's a perfectly acceptable method. So the goal is to learn to take enough actions in order to maximize the reward. Let me say that another way. Make enough mistakes, fall off the road enough, which you'll see in a moment. And when you eventually learn not to do it, so you've got the camera here and you're learning when you roll off the road, you keep doing that, just like that, just like the gazelle that I mentioned earlier. Eventually, it learns to stand on its own 2 feet. 30 minutes later, the thing's running 20 miles an hour. How did reinforcement learning gain prominence? A group of Google, which everybody I'm sure has heard of DeepMind. Lee Sedol, pardon me, was beaten at Go. Reinforcement learning, the algorithms for Markov decision process, the Bellman equation were written in the 60s. Let me say that again. The algorithms for reinforcement learning were written and designed in the 1960s. Okay, we just didn't know what to do with it. We had no idea what to do with it. This, to me, AI, reinforcement learning is really a pure form. You'd have people argue with me about this, but it is a pure form of artificial intelligence. It truly is, because I'll say it like that. I think I might be less offensive if I said it like this. If I said the actions used in reinforcement learning more closely mimic human learning behavior than other areas in artificial intelligence. I think it's fair to say that. Think about a car. The car is learning, it's taking pictures as it's driving, and it's learning not to fall off the road. Again, I'm gonna keep rehashing this, because I'll tell you one thing, and I'll pick on the industry for a little bit. When I first got into reinforcement learning, and now I think it's been about a year and a half that I've just focused almost solely on reinforcement learning. The explanations I found just really, I can remember the first time I looked at it, I walked away and I thought, I have no idea what this is doing. I have no idea what it's doing. And I guess just my personal understanding of it, or the literature has gotten better, because this is quite a hot topic, particularly because of self-driving vehicles. But it helped me to continue to go over this, because what I'm about to show you here will resonate when we get into looking at the car specifically. Okay, we have an agent. That's our car. And then we have the environment that the car in. This is our track. Okay. Select action using a policy. Think of the policy as the algorithm. Okay. Think of the policy as the algorithm. That's what it's designed to do. Okay. So the agent has two choices. It can run off the track, or it can stay on the track. If it runs off the track, it's negative 50 points. Okay, it's bad. Next time, don't do that. And then the policy continues to update. You're going to see in a moment when we do an actual. We're going to fire up an AWS console in just a minute, and you're going to see exactly how this works. You're going to see a simulation of it, which is really cool. So you're seeing that it's updating the policy, and it's iterating until the optimal policy is found. So that's what it's doing. Again, the agent, the vehicle, the environment, you get burned, you fall off the track, or you don't. And then the policy iterates and updates. Here are a couple of examples: Land Rover, Range Rover, whatever you want to call it. A game, which what I'm going to show you guys is teaching optimizing a reinforcement learning algorithm to play a game of your choice. There's there's a library that allows you to do that. So that's what I'm going to, at the end, that's what I'm going to leave you with, to say, if you want to try this, here's a perfect place to do it. You could monkey around with the code and have it going this afternoon. Okay, all right. This is the only math I'm going to throw at you guys. The Markov decision process is really the mathematical formulation of a reinforcement learning problem. The math behind reinforcement learning is deep. It's a deep topic. I just swath through it every day, and again, the power behind it. There's quite a bit of math behind it. So what we're saying with the Markov decision process and the Markov property, that only the present matters. Okay, so it does forget. So that hence having to be reinforced. So a lot of what you'll see with the math behind reinforcement learning is part of the Markov decision process. And these are some things, some nomenclature that you'll see. And it falls in line with what we've somewhat discussed. S is a set of possible states. Is the vehicle moving? Is it moving? Is it stopped? Is it off the track? Is it on the track? A is a set of possible actions. R is the reward given. P is a transitional probability. And then the discount factor adjusts the memory. So that is a very crude, down and dirty, just acknowledging that we're using the Markov decision process. I'm by no means am going deeply into it, because I think that defeats what we're trying to accomplish today. Q-learning is, this is going to be the last bit of math and algorithm that I show you, but Q-learning is also the way that the algorithm learns. And I'll go through this real quick. You have the old value times the learning rate. Think of stochastic gradient descent there with the learning rate. The reward, the discount factor, which adjusts the memory, and the estimate of the optimal future value. So if you hear the term Q-learning discussed, that's what Q-learning is. Now, this is a little different from what you're accustomed to seeing with the mean squared error, root mean squared error, where you want the error minimized. Okay, so let's think about, and with reinforcement learning, we want the reward function maximized. That takes a little bit of getting used to, but that's an important concept, and I've got an example of what I mean by that. Okay, this is great. It's really cool to ride these self-driving cars. It's really cool to be able to optimize Miss Pac-Man. But let's talk about some practical implications of reinforcement learning applications in the industry. That's truly what matters, and there are going to be a couple that you might not have thought about. A big one, different ways to use reinforcement learning, is supply chain management, demand forecasting, fleet logistics. It can be used in agriculture. I believe Amazon Web Services uses reinforcement learning to adjust the cooling in their data centers. That's one area. Of course, robotics. Robotics stands out because it seems to be the most obvious. Anytime you're seeing if you're seeing any robotics today, typically there is going to be some level of reinforcement learning behind it. My area right here, again, is autonomous vehicles. It's also used in HVAC, which that's air conditioners and so forth, wind turbines, and robotics. Supply chain risk management. I mean, I considered doing a project with a company, wasn't able to because I've got too many other things that I'm doing, where they wanted to evaluate their supply chain by making a virtual environment and using reinforcement learning to simulate their supply chain. But that right there is a fantastic use of reinforcement learning to address the supply chain and just different ways to do that. Okay, I'm going to stop sharing this screen and we're going to move to another one. While I'm doing that, any questions? You guys have any questions before we move on to anything else? How is that sinking in? Is it sitting in okay? Yeah, okay, good. Okay, now we're going to get into the, now let's get into the specifics with the DeepRacer. Some of what I'm about to go over might sound a little redundant. If so, that's done on purpose because, again, this is a heavy topic. I mean, this is a heavy topic, and the skill in doing a presentation on something like this is to make sure the audience walks away, understands it, and is motivated to move on to it. There's no way we could be totally comprehensive with it.
And we do have a question in Slack. I don't know if you're in the Slack channel right now, but
yeah, I actually am.
Okay, great.
Actually, the opposite of that. The question is, so most applications would be where constraints are well defined, and the answer is reinforcement learning works better when there are no constraints at all. They work better when there's no constraints at all. In fact, there's a name for it. It's called modeling or non-modeling. If it's a non-model, that means it's just strictly trial and error. So with the car, you almost would have no algorithm written at all. The car would just learn strictly by trial and error. So to succinctly answer the question, reinforcement learning needs absolute no constraints at all. Let's see, second question. Does reinforcement learning always include an element of time that we learn in, or there are other variable spaces? Time, of course, is a component. If you look at some of the algorithms for a self-driving car, you'll always see the sub T1, sub T -1. So it almost always presumes that there's going to be some time element associated with it. And again, it being just a pure form, in my judgment, a pure form of AI, it can pick up whatever time frames those are. Good example of that is the stock market. Interesting, because you can look at trades that are being traded in milliseconds. If the tick data is traded in milliseconds or in seconds. It's very responsive to that. Let's see. Hey, how much do you find that some concerns with positive and negative reinforcement learning apply to machine learning as well? That's a really great question. I wish I had more time to talk about that, Carl. You have biases, and we have human bias in anything. It's a huge issue in the industry. It's a big issue in industry. One of the things that, and a lot of that is like this. I mean, think of it like, I guess one way to think of it is consider data collected. Consider data collected from a sample that goes into a CSV file where you, probably better than that, a natural language processing problem, which I have no expertise at all in. Think about, but I do know this. I know there's all kind of human bias in that, in a natural language processing problem. With self-driving cars, it's kind of, I think it'd be different, specific to self-driving cars, simply because the car doesn't discriminate. It truly does not. But here's an error. Let me give you an example of a problem with a self-driving problem that you have when you're collecting data with a self-driving car. All right, so Noel and I are in our self-driving car, and we're in Denver. I'm in the passenger seat. Noel's sitting there in the driver's seat with the car's driving. What do we do if we come to a stop sign? If the car has been fed enough data properly, we see a stop sign, well, it stops. Well, we come to another stop sign. That stop sign's dirty, okay? Well, we still stop, okay? What if we move to a stop sign and half of the S is missing? Then what happens? Well, if the vehicle had never seen that data before, then Noel and I are going to run a stop sign. Those are inherently human type errors that you could get with something like reinforcement learning. So is it there? Certainly it is. Is it there? Is it as prevalent as it might be in natural language processing? Yeah, I could get an argument out of that. I'm reading what you said right here again, but I personally don't think it is. Yeah, okay. Yeah, I guess, Carl, and that question is that's a possibility. I mean, I think that could happen, but I think that would be bad science to do that. If you're trying as much as you can to allow a car to drive, then you don't want to put as much human input there, because it. I mean, I personally wouldn't have. I've personally never done what you're describing here before. I've just really let whatever data that I've had be part of the model. That probably wasn't a good answer, but negative reinforcement really doesn't work on cats. Interesting. I guess I could take this a step further and see if I could try it with my kids, because they tend to reinforce bad behavior. Okay. I'll come back to any other questions you guys have, but let me move to, I'm going to move to this right here. Move along to this. Noel, did you guys in your course, have you used Amazon Web Services?
Yes.
Awesome. Okay, we're on Amazon Web Services right now. And here's what we're going to do. If you go to, with AWS, go down to Machine Learning, and then go down to DeepRacer. Go to Get Started. Now I'm going to create a model for you guys. I'm going to create the model, let it start. It takes about 6 or 7 minutes to get going. We'll come back to it. But in the interim, I'm going to go through and talk some specifics on reinforcement learning with self-driving vehicles. But let's go ahead and create a model. We'll name it GA Stroud. Okay. And then we could use a track. We'll just use this right here, use Roger Raceway. So it's going to train on this track right here. Okay. Now, one thing that I'll say this, if you have your, I'll come back to that in a second. But this is a track it's training on right here. Okay. And we'll do a time trial. You can also do object avoidance, where you put stuff on the track and you would want the vehicle to go around it. Or head-to-head racing. Your agent is your car. You can even calibrate the car. In fact, you're supposed to. I've calibrated this vehicle. Okay. Now here's some specifics in here of the code. This is where I would start to make the changes in here for different algorithms. Okay, we're going to use the default algorithm here, but you've got a couple of things here, like for example, for these reward functions, and this is just nothing more than a Python function. You give a higher. We're just doing one for this simple example, and let me walk through the code for you real quick. You give a higher reward if the car is closer to the center line. So it is rewarded, it gets a higher reward being closer to the center line. And this is the track width, these variables that you've declared right here, are the track width for marker 1, 2, and 3, and just a very simple if-else statement. So if you're closer to if your distance to the center is close, you get the highest reward, which is 1. It's a little further away, you get half a point. Further than that, you get 0.1. And then if you crash, you basically get 0. Make sense? That's a very simple algorithm, simple reward system. You can get extraordinarily complex with this, and this is where a lot of my complexity comes in, where I write code here. As a matter of fact, what I've been doing is writing the code in C++ to make it even faster. Okay. This training algorithm right here, this PPO, is a gradient policy algorithm which uses gradient ascent, not descent. I will post a paper on this PPO here, a little more information about that. And just like you would see in deep learning, you've got hyperparameters where you can adjust. Using 10 epochs here, here's our learning rate. 20 episodes per policy updating. I'll show you what that looks like in a minute. We won't be using any stop conditions. And in terms of cost, AWS gives you 10 free hours, but to train for 1 hour costs $3.50. So let's create the model. Okay, we're going to come back here in just a second because it's preparing to get ready to train, and you're going to see something really cool when it does that. So right now, let me switch over to another screen. Can you guys see a screen that just says what is reinforcement learning? Can you see that? Okay, I'm going to go through this specific, very specific to self-driving cars. Whereas before we were speaking generally about what is reinforcement learning. We did that the first pass. Here's the second pass. This second pass is going to make this stick for you a little bit. So again, here's our agent right here. Someone said Wally E. That's not bad, but I just really got to come up with something good. I just can't find it. So our vehicle is the agent. Our environment is the racing track. And what happens is, again, the agent takes actions in the environment and it feeds back to, it keeps somewhat of a feedback loop going. And the vehicle just, what of course it wants to do is improve the reward. It continues to get experience, and not running off the track gives a higher reward state. Can you guys see this other screen here? Did it just move over? Okay, again, so the agent is the DeepRacer. This car is referred to as a DeepRacer. And that's what we're using in simulation. And what we're going to do with this is, well, let me get to that in just a second. So here's the agent, the vehicle, introduce that nomenclature. The environment, as I've said before, is the track. Now, what happens is you're about to see a virtual track in just a second, okay? What I've done in my home is I've built my own track. So what happens is a virtual track that you're about to see does the training. The training is done on that track that you're about to see that's still initializing. Okay, so it's done on that track, and when it's finished training, I will adjust the parameters and then test, and then once I have the algorithm where I want it, then the software, the training software is downloaded to the vehicle. I put the vehicle on the track that I made, and it just goes around the track. That's the whole process. That right there is the entire process of how it works. The state is the track, okay? And it's caught by the cameras, so the track has cameras that it's using. And then the actions, the steering. Steering and staying on the track are the particular actions that the vehicle makes. And then the reward not falling off the track. So ultimately, what you want to do is have the vehicle not fall off the track, and it's rewarded for that. Training, as we said, is an iterative process. So let's talk about what that looks like. So here we have the DeepRacer here, and here we have a straight line track. And this gets into the reinforcement learning side of it. This right here, what I'm about to show you is, hang on, let me check on what this is doing here. I'll come back to it in just a second. Okay, now we're going to get into into the reinforcement learning side of it that I think is one of the better explanations that I've ever seen on reinforcement learning. Okay, so we have a very simplified environment here, and we have the straightest path with the vehicle, and then the finish line. Okay, so if you assign a score, if you assign a group of rewards to a self-driving car, you get the highest reward. Think back, did you remember seeing that function, that Python function a moment ago that gave the 1 for staying on track? It's closest to the yellow line. The same thing here, okay? If you just stay straight in the middle, you get 2 points per grid, per square. If you veer to the left or to the right, you get 0.2 of a point. And then if you just fall off the track, you get an X. You get nothing. And it looks like this. So here, let's look at it again. Right here, you end up getting a total of 2.2 before the vehicle starts again. So the vehicle's running, it's driving, it's 2 points, and then 0.2 of a point, then it runs off the track, and then it's punished. So it gets somewhat of a reward, but not much of one. All right, I will come back to this in just a second, okay? All right. Now, back to the story of the colt, or the colt gazelle. This is doing the same thing. The colt comes out of its mother's womb and it's trying to move. It's trying to figure out how to walk. And eventually it's able to run 20 miles an hour. Same thing here. 2/10 of a point, it falls off. Here, a little more, and then it falls off. So it's learning. And this is the exploration side of it. It's not the exploitation, but you remember me talking about that in the beginning, exploration versus exploration versus exploitation. Remember the story of the Tour de France drivers. So right here, it's exploiting what it's exploiting this behavior, and it's seeing that if it doesn't hit these X's, it scores higher. And then eventually you have convergence, where it does it every time. And then eventually it figures out, instead of going, let me show that again. Eventually it figures out, just go straight line, you get more points. Now, if you wanted to get into the X and Y's of the parameters of the vehicle, this right here, and this just is very much calculus to me. Here's how you see the parameters right there, with the positions on the track. That's what it looks like. Same thing with the heading. You've got these sensors. You've got the cameras and the sensors that are determining that for you. Waypoints are basically each tick, one to the next, to the next. That's where the time series that someone asked me about earlier. Track width. So one thing you have to do, I build my own tracks. Most people do. So when you build your track, you have to make this mathematically precise. So I break out a protractor and a compass and everything. You have to do that to make this work right. Noel, are you laughing at me? I don't blame you. It is funny to watch. Distance from the center line, we talked about that. You get more points by staying on the center line. All wheels on the track, that's a good thing. Then speed, this device can go about 9 miles an hour, which is faster than you think. Steering angle, and there's a summary of all the parameters. These are all, think of these as parameters that can be optimized and adjusted. So you can use all of these as part of a reward function. Okay, now for the cool part. Can you guys see this? All right, think of everything we talked about. Watch it. This takes 60 minutes. Watch it going slow. Not really sure what it's doing yet. Going slow. Now it's on the yellow line. That's what it's supposed to do. It gets us 1 point. Think back to the code. 1 point, 1 point. It keeps getting, because it's nice and close. It's going really slow though. A little off the center. This is actually training pretty well. This is 11 minutes into training. This is what we set up a moment ago. It's 11 minutes into training. It's doing really well, actually. Noel's my good luck charm. Maybe that's why. Okay. Points taken away. Think with the X. Now it's going to go off. Almost. It's about to. There we go. Now it starts over, okay? Is that cool? So think about everything we talked about, everything we've talked about, the math behind it, the Q learning, the Markov decision process, the environment that we're in is the track. The action is moving. And then we have the agent, which is the vehicle. It's doing everything we talked about right there. See, it just ran off the track. Now, if you look to the right, or rather to the left, you can see that the best that it's done, let's refresh this. It's only, the best model has only gotten through the track, only gotten through 38% of the track. See that there? So it's got a ways to go, but we're 12 minutes in. We're 12 minutes in, and it has another 48 minutes to train. So what happens is when this is finished, I don't have a track made for this, but let's presume that I did. So when this is finished training, then I would take it and optimize it. Once it's optimized, then that training model is loaded to the vehicle. It's loaded to the vehicle wirelessly. I turn the vehicle on, put it at the start line, and it drives itself. Self-driving vehicle. And that's it. And all of this is done with Amazon Web Services. Before I get to the resources that I want to show you guys, so you can go and do some of this yourself, I'm going to pop over to Slack. So is this, thank you, Gwen. Yeah, that's good. Roll E, Carl, that's pretty good, man. I like that too. Is this in real time? Yeah. Yes, it is. Yeah. Yeah, this is, can you guys see the whole screen? I've got Slack up in half of it, in half my screen. And it's interesting to watch this because when you start thinking about the stuff all the material that we covered prior to this, it is really something else to see it in motion. And what is to me just phenomenal and fascinating and more satisfying than I should admit is when you do a model, and then you load it onto your actual vehicle and watch it go. I mean, it is freakish to see that. And then when you think about the algorithms that are behind it and making it better, then that's even more satisfying. I would take the position that those that have something tangible like this end up having a better grasp on reinforcement learning. I mean, from this point on, you guys, when someone asks you about reinforcement learning, I feel like after the time we spent together, that you're going to be able to pretty quickly say, yeah, you know, I've seen what you can do with a self-driving vehicle and exactly how that works. And I feel like you've got a much better understanding of it than someone who sat through a presentation that where you were discussing the Bellman equation and double Q learning and those items, which those are fundamentally important, obviously, but once you get a grasp of what's going on here and you start thinking about, I'm taking this vehicle, this training in the cloud, and then I'm going to put it into a physical vehicle and put it on a track and watch it go around, it really motivates you to want to learn. All right, look at what it's doing right now. A little bit of erratic behavior. You see that move there? This is a harder track, so it is more erratic. If we had just a track that was a very, very simple, more simple track that just made somewhat of an almost an oval shape, it would be easier. But this right here is a more difficult track. I think that's why I was having problems training. It's speeding up and slowing down. And Mario Kart has funny. Okay, before I move on to anything else, any questions about this? Was this cool? Was that cool? Before this car came in, it was embarrassing how much I was tracking that vehicle before I got it in the mail. Let me see what you guys are saying in here. Hang on. Does RL always lead to an optimal solution? No, it never does. I don't think there's anything that does. That's a great question. And no, there's no. The Bellman equation is where you would look to find your optimal solution, and no, it would be the same as having an R squared of 1. You know, it just wouldn't happen, and it probably wouldn't generalize well. Any other questions before I move on to something else that I was going to show you guys? I like the names. That's really good. You guys have done a nice job there. Okay. Let me share something with you that you guys can walk away and start doing today, okay? One on my GitHub, let's see. I've got a repository here for reinforcement learning research. Put that in the chat. It's on, I just put this in Slack. That's a good way to keep up with what I'm doing with the code that I'm writing in reinforcement learning, so you can get a sense of what I'm doing. But here's something that I really want to show you guys, and I'll put this in Slack as well. Okay. Can you guys see the screen? Okay. Now, this is something you can do this afternoon with reinforcement learning, okay? Like I said, I wouldn't feel good about myself if I came in and showed this car and made myself look like I'm the only one that had fun with it. I'm about to show you some code as well that I'll share with you that I may have already shared it with you, where you can go ahead and start testing out some reinforcement learning algorithms. GEM OpenAI is a toolkit for supporting reinforcement learning. And what you can do is you have access to games like this right here, like Cart Pole, Random Agent on Ant VW, Space Invaders, where you can use a reinforcement learning algorithm to teach these games how to play, just like they did in Go. You teach Go to play better than the human, okay? Now, one thing that's interesting, I think someone asked me this, someone kind of asked a question this way earlier. If you based, how did the reinforcement learning algorithm beat the best player at Go? Well, the reinforcement algorithm didn't take the best player's moves into consideration. okay? It didn't use a model of his moves. If it did, and I hope what I'm going to say makes sense, if it did take the player's moves into consideration and use that as an algorithm, then the policy or the algorithm would only be as good as the player. Does that make sense? But if you taught the vehicle, or rather if you taught the algorithm to play on its own, then it gets as good as it can get, as good as it can possibly get, as good as it can, as well as it can be optimized, might be another way of saying that. So that's what you're doing with reinforcement learning. If you weren't doing that, it would be more like supervised learning. Here's some of the code that you can use to get started right here. This is just a good boilerplate code right here to get started. But what I'm going to show you, and I've shared this code with you, is in fact the code is with that GitHub. If you go to General Assembly, you'll see that code in there, which that I'm about to share with you, which is this. Can you guys see a Jupyter Notebook? Okay. All right. One thing that, and this, no one's asked me this, but it'd be a good question where you would say, well, okay, I'm used to having data. I'm used to having a spreadsheet, CSV file. I'm used to being able to access a SQL database. I'm used to being able to access photos, text, or something. Now, this reinforcement learning you're talking about doesn't have a, quote, data set. Well, for the most part, that's generally correct. So what you're going to have with this OpenAI, and this code right here is using OpenAI, okay? Or GEM, I call it OpenAI, but it's actually GEM. You're using the GEM library. And of course, you have to install it like you would any other package. And here's some Python code that should get you going. One easy way to run it, if you want to, and I would ask that you guys, if you would, because I like to see who's following, please follow, let's see, please follow and star this, that GitHub repository, if you would, please. I like to see who's on it, so if you would, star it and feel free to download it as well. Once you do that, if you really want to make it easy on yourself, I have it set where you could run it in Colab right off the bat. You shouldn't have any problems with that. Boilerplate code here, I am using TensorFlow. If you have a GPU, it's going to run faster. No, you guys know in Colab you've got a GPU. So you could run a GPU in Colab with this, which that might make it kind of fast. So here I'm importing GEM. This GEM environment tells me all of the different games I have. Here's some nomenclature to make the cart pole game. That's what we're using there. For the environment, GEM, make cart pole. I've documented this code pretty well, so you can read through it at your leisure. This right here would be based on you having a Windows computer or a Mac. I almost would say take advantage of using Colab. You might have more success there. Okay, so right here is what this game looks like here. Okay, and you'll see the game is to hold the stick up and it moves from left to right for the cart pole. And it goes through a couple of things, like a simple hard-coded policy, which you can just read this code at your leisure. I'm not going to walk through all of it. This is just a simple hard-coded example. Little slow there. And then it gets into more detailed examples like neural network policies, which you can read more about these. I'm using Keras for this. Again, it's documented pretty well. And basically what I'm doing is I'm just making the models more sophisticated as I go. Policy gradients, here's some information on policy gradients, one of the more important parts of reinforcement learning. Markov chains, and some information about Markov chains. The Markov decision process, which we talked about. Q-value iteration, I showed you an example of that earlier. Q-learning, deep Q networks, and so on and so forth. We're closing in on time, so I'll let you guys just at your leisure look through that code. And again, all you have to do is clone the GitHub repository, and it's in the General Assembly file. And then I have all kind of different codes there, all kind of different code there if you want to look at it. And different reinforcement learning resources. So this is, I stay up with this pretty well. So anything that you want to look at reinforcement learning based is in this repository. That's a lot of material to cover for one day on a Friday afternoon. That's a lot, but you know what I would say, and I'm going to open the floor to questions. So what I would say is follow what's going on my reinforcement learning GitHub page, and feel free to look at Amazon Web Services DeepRacer. I think we covered that pretty well. And all of my information is on there. My email on the PowerPoint that I shared on Slack early in the week. All of my information is on there. Feel free to reach out to me anytime. This is you can ask me. Well, this is all I do is reinforcement learning. So I'm happy to talk to you guys anytime about this, and I will open the floor up for questions. I'm looking at what you guys are saying on Slack. But any questions? Physical conditions like gravity. Those are things that. Okay, the question is, are there physical conditions like gravity or things that might be taken into consideration when I guess when you're looking to build a model? I'll go back to the story about Noel and I riding around Denver, and we run into a stop sign. Well, if our model has never, and this gets back into, again, overfitting a model. And, again, kind of going back, I always say everything goes back to linear regression anyway. Let's go back to linear regression. We talk about being able to have a model generalize or fits the data too closely. If the model didn't generalize well, then it wouldn't recognize that stop sign. So those are things that you have to consider. Reinforcement learning is the most data hungry of the disciplines. We need more data. We need we need as much data as we possibly can, especially in the self-driving world, because it's happened a few times already. But imagine when we have wrecks or fatalities due to a self-driving car. It's happened a few times already. And think about things like this. I have friends in the insurance industry and have asked them, how are you guys planning on dealing with the insuring cars that are self-driving cars? And they don't have a good answer. I mean, it's something they really keep kicking the can down the road a little bit. They want us to mature the industry. Me personally, if you look at companies like Mercedes and Hyundai and so forth, it seems like 2030 is their year when they expect us to really have our stuff together. Yeah, I have a friend who has that's Andrew Ng, one of his, in fact, this is kind of an early reinforcement learning paper where he was doing some research with a drone, or it wasn't even really a drone, it was a plane. So I don't know. I can't speak to that well enough. Did I miss any questions? I see a lot of writing here, but did I miss a question? Someone's. Ooh, yeah, I had to train a Mars rover with reinforcement learning. That's what you would do. I mean, that's what you would do. How would you simulate the environment? Man, you know, it is really, it's really interesting that I say to myself and to my kids and anybody else that I said to Noel as well, I want to live longer so I can see what's next. You know, I want to see what's next. And right there, pursuing that's, yeah, man. I mean, really, who wouldn't want to be part of that? That's huge. How do you simulate that environment? It's a great question. You know, again, I mean, the statement that I would make is, I wish I could be around long enough to see that. Perhaps if I'm reincarnated. One more question coming. Let's see what this says. While I'm waiting for that other question, was this helpful? Did this get the point across? You know, the space of just career advice. You guys have been trained by the best. So go out there and practice, because this is, I've always said, the world of data scientists is kind of like the group and world of people that are involved in this industry are kind of like those people that followed the Grateful Dead around years ago. They refer to collectively as deadheads. So we're like that, just without the drugs. I've always said that. We're a unique group of people that are very curious, and I am proud to say that the majority of us love to share information. Noel and I have learned so much from each other, and just know that people in this industry are like that. And I would feel good about knowing that you guys came from Noel. I would feel good about hiring any of you. So keep working hard, stay curious, stay in touch with me, friend me on LinkedIn. And is caffeine a drug? No. No, it's not. The only complaint I have at the university that I work with is we have a computer lab where I lecture, and they don't allow any drinks, which means that I can't take coffee in there. And I really I've talked to my lawyer about this and asked if we can get some type of provision for me to. I'm kidding about that, but I would, because I go in there and my lectures start at 8 a.m. and no coffee, and I just think, my God, I mean, you know, either let me have coffee or give me a raise. One of the two. Caffeine pill hype? No, no, man. I'm weird about the coffee. I mean, I like grind my beans and stuff. I'm weird about that.
All right. Well, thank you so much, David, for your time and for sharing your knowledge with us. We really appreciate it. This was really helpful.
It's an honor to be here with you guys this afternoon. Noel, thank you so much for your kindness, and for you guys, I wish you the best of luck. Please stay in touch. Please let me know if you need anything, and good luck.
Awesome. Thank you. Bye, everyone.
Bye-bye.